This is Chapter 2, number 41. It's an American folk song. I'm only going to focus on the bottom two stanzas here because they're the only important ones. So, we're trying to find Goff's hourly wage. The foreman's name was John McAnn. By God, he was a blame me man. One day a premature blast went off, and a mile in the air went Big Jim Goff and drill. Then when next payday came around, Jim Goff $1 short was found. When he asked what for, came this reply: "You were docked for the time you were up in the sky." So to figure out Goff's hourly wage, we know that he was docked $1 because he was in the sky for some amount of time. And we know he went a mile in the air. So if we figure out how long it takes to go up a mile and back down a mile, then in seconds, and divide that from $1, we'll get his wage in seconds, his secondly wage, and then if we can convert that to an hourly wage. Assume that air resistance may be neglected. We know the acceleration due to gravity is negative 9.80 meters per second squared. The negative sign is to show that gravity is pulling downward. During the flight, Goff went 1 mile, which is 1,609 meters, up, and then 1 mile back down. We will begin by determining his speed just after launch by considering his upward flight, using the given equation. The final velocity squared is equal to the initial velocity squared plus twice the acceleration times delta y. We're trying to find the launch velocity, which is the initial velocity vi. We'll plug in what we know. We know that the final velocity is 0 because he is at the peak of his flight. We also know the acceleration of gravity is negative 9.80 meters per second squared, which is why the positive sign is now a negative sign. We know that he went a mile in the air, which is his final height, y final, 1,609 meters. And his initial height is 0 meters because he starts on the ground. Simplifying, so while solving for vi, we get here. Then we take the square root to end up with 178 meters per second. Goff's time in the air, then, may be found by considering his motion from just after launch to just before impact, which means just after he took off to right before he lands. To find the time, we will use the equation y final minus y initial, which is delta y, the change in height, is equal to vi, the initial velocity, times time, plus 1/2 the acceleration times time squared. Let's plug in what we know. We know that the change in height, delta y, is 0 because he's landing from where he took off from. We calculated his initial velocity vi earlier and found it to be 178 meters per second. We're trying to find time. We plugged in our acceleration due to gravity, negative 9.80 meters per second squared, and now we will solve for t by factoring out t and then finding the roots of the equation. One root, well, the root will describe his times when he's on the ground. There's 2 times where that happened: his takeoff time and when he lands. The takeoff time is obviously t equals 0. The landing time can be calculated by setting this portion equal to 0. And you will end up with t is equal to 36.2 seconds. Now that we know the time, we can find his rate of pay by dividing 36.2 seconds from $1. That will give us his pay rate in seconds, $0.0276 per second. We want his hourly wage, so we will use dimensional analysis and multiply the problem by 3,600 seconds per hour to get his hourly wage, $99.30 per hour. Lastly, we have our assumptions. we have assumed that the workman's flight time, a mile, and $1 were measured to 3-digit precision, or to 3 sig figs. We have interpreted up in the sky as referring to the freefall time, not to the launch and landing times. Both the takeoff and landing times must be several seconds away from the job in order for Goff to survive to resume work. There is an alternate method to solving the problem. We know, since he lands where he took off from, that the time it took Goff to fly a mile up in the sky is equal to the time that it took him to land. Likewise, the time that it took Goff to fall from a mile up in the sky is equal to the time that it took Goff to reach that height after takeoff. Therefore, we can calculate the total freefall time by doubling the time it takes Goff to reach the ground, starting at a mile in the sky standing still. He is without motion because he is at the peak of his flight. To find the time, we will use the equation y final minus y initial, which is delta y, or the change in height, is equal to the initial velocity times time, plus 1/2 the acceleration times time squared. Remember, we are using this equation to calculate how long it takes Goff to fall to the ground starting at a mile in the sky. He is standing still because he's at the top of his flight. Let's plug in what we know. We know that his final displacement, his final height, is 0 meters because he is hitting the ground starting from his initial height of 1,609 meters in the air, which is 1 mile. We know his initial velocity is 0 meters per second because he is starting at the top of his flight, in which case he is not moving. We also know the acceleration is due to gravity and that it is negative 9.80 meters per second squared. Now let's simplify each side of the equation. We end up with negative 1,609 meters is equal to negative 4.90 meters per second squared times time squared. Now we solve for t squared. We divide both sides by negative 4.90 meters per second squared, and then to solve for time, we take the square root to get t is equal to the square root of 1,609 meters over 4.90 meters per second squared. Remember, this is only half of the total freefall time because we were finding the time it took him to fall from the top of his flight a mile in the air. To find the total time, the time it took him to go up a mile and back down a mile, we just double this. So his total freefall time is equal to 2 times the square root of 1,609 meters divided by 4.90 meters per second squared. And with that, you end up with 36.2 seconds, just as before. It's the same from there as before. To find the pay rate, divide your time in seconds from $1, which is how much money he was docked for on his paycheck for the time he was in the air. You will get $0.0276 per second, just as before. To find his hourly wage, use dimensional analysis to change seconds to hours, multiplying by 3,600 seconds per hour, to end up with the final and same answer, $99.30 per hour. The assumptions used in this problem, in this method, are the same as the previous method.